Hey, science nerds, and welcome to our second discussion about electrical and magnetic fields, topic 1.2, which is equation for fields. Last time around, I discussed field lines, discussed basically how gravitational fields, or what a gravitational field is, or what an electrical field is, or a magnetic field is, and how field lines can determine the direction of these fields and the relative magnitude or strength of these fields. Today, I want to give you some equations. There are going to be four equations that are going to be coming at you today that are going to allow you to calculate either the field strength or the force that is being exerted by a field. We're going to concentrate our equations today on gravitational and electrical fields. There won't be any equations for magnetic fields today, but I will discuss magnetic fields at the end of today's lesson as it pertains to the planet Earth. And I'll get to that as sort of my last topic before I finish up today. What should you have with you? You should have a calculator. For sure, you're going to want a calculator today. You're going to want your data sheet on page 2, specifically page 2. Most of the equations are going to be there. In fact, all the equations we're dealing with are there today. And I would also recommend you've got the notes on a separate window, maybe beside this video or on a separate device. I'm going to give you examples directly from the notes, and I'm going to, you may want to cover those pages up when I get to those pages. When you see a page that has an example, just maybe cover the answer and just be able to see the question on that page. I will not be writing that information on the whiteboard today. It's just there's too much material to do that. I will refer directly to the notes for those questions, and I will walk you through the questions that are on those note pages. Okay, so let's get started here. First, we'll discuss gravitational equations for gravitational fields. The first equation I like to deal with today is something called gravitational field strength. Now, gravitational field strength, and I'm going to read this directly off the notes so I don't get it wrong, because I'm not a physicist. You know, I'm more of a bio guy. But the field strength is determined as the number of newtons per kilogram a test body experiences at a given location from the mass of another object. That's gravitational field strength represented by little g. Now, what does that mean? Well, let's take an example here. What's a test body again? Well, a test body I talked about last time in 1.1. It's any object that if you put it into a field, that it can actually show that it's having a reaction to the field. So if this is a gravitational field, for example, let's say I'm going to use this pen as my test object, how much gravitational field strength is being exerted on this pen from the Earth that's directly below me. This would be the test body. The Earth would be the object exerting the mass, or exerting the gravity, because it's got much larger mass. Remember, the pen is also going to exert gravity on the Earth, but because it's so much smaller, it's not going to have anywhere near the gravitational field strength that the Earth does directly below it. But be aware of that even though if I drop this pen right now and it's going to fall because of gravity, it does exert gravity on the Earth. Very minuscule amount of gravity, but it does exert gravity because as long as it's got mass, you understand that any object in the universe that has mass is going to exert gravity. But in this case, if I wanted to calculate the gravitational field strength right here, right where that pen is, what I would do is I'd have to do a couple things. First of all, I'd have to calculate the mass of the Earth. That would be my first step. So the mass of the Earth is right here. M is in the equation. That's the gravity that's the mass of the object that's producing the gravity, and that would be in kilograms. All right. Then I would also need to calculate the distance of the pen from the Earth. So I'd have to measure this distance down to the floor here because that's essentially the Earth at this point. That distance would be my radius, which would be measured in meters. So that would be the distance from my test body to the object that's producing the gravity. And in this case, I'm specifically asking what the gravitational field strength is of the Earth. I could ask the question, what's the gravitational field strength of the pen? I could. Then this would become the object that has the mass. The radius would still be the same, and then my test body would technically be the Earth, which is, kind of weird, but that you could play the equation around on itself that way. And then the last variable of the equation is capital G, which is known as, hold on, I've got it right here. That's the gravitational constant, which I'll get to here in a couple of seconds. A couple of things to keep in mind, though. And the equation, I'm going to read through the whole equation because I haven't actually officially said the equation. The equation for gravitational field strength is capital GM divided by radius squared. That's basically the equation. Again, it's on page 2 of your data booklet, so you don't have to memorize it. But what are some of the things that we should keep in mind? Well, the mass is going to be directly proportional. The mass of the object producing the gravity is going to be directly proportional to the strength of the field that it generates. The bigger the object, the bigger the gravitational field strength is going to be. But if I increase the distance of my object, my test object, from the object that's creating the gravity, in this case the Earth, the further away my test object gets from the Earth, the smaller the gravitational field strength gets. I mean, if I put this pen 100,000 kilometers outside the Earth's in space somewhere, it's not going to be falling down to Earth right away. There is gravitational field strength up there, but it's not anywhere close to the gravitational field strength here, that it's only like, about 1.5 meters away from the ground. So that's how this equation works. And again, there is what we call this universal gravitational constant, which I'll get to. This universal gravitational constant, again, is on page 2 of your data sheet. It's right there. You don't have to memorize the number, but this is the number you have to plug into all of your gravitational field strength equations, no matter where you are in the universe. This is just a constant that was actually created. It was originally proposed by Newton, and it was actually calculated by another English scientist by the name of Henry Cavendish. If you want to see a little bit about Henry Cavendish and how he came up with this number, watch the video. It'll explain sort of how he came up with this constant number. But the number, just so you know, is 6.67 times 10 to the negative 11th newtons meters squared divided by kilograms squared. Again, we don't have to memorize it. You just have to know where to find it in your data booklet. But this number is always going to get punched into your equations. You can see why now if I've got the mass of the Earth, which is going to be how many kilograms? Holy smokes! Hundreds of 5 times 10 to the blah 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 blah, whatever the number is. You realize our numbers are going to be huge. You definitely need a scientific calculator here. You have to be able to do scientific notation with these. You have to be able to do it. You have to be able to use your calculators properly. These questions can really burn you if you're not plugging in the numbers correctly. Very straightforward equations, but the numbers are so onerous that it can be a problem when you're punching them into a calculator. But this is basically it. You've got your gravitational field strength, which is in newtons per kilogram, is going to be equal to your universal gravitational constant, which is 6.67 times 10 to the negative 10 to the negative 11th, newtons meters squared per kilogram squared. Then I'm going to multiply that by the mass of the object's gravity. I'm going to calculate that by multiplying the mass of the object that's producing the gravity, and then I'm going to divide that by the radius squared, which will be the distance from the object that's creating the gravity to the test object that is in its gravitational field, and that's going to be squared. That will give us our result. Again, everything you need to know for this, page 2 of your data booklet. Let's try an example. Let's try a couple of examples of this. Next slide, if you're going to flip it, don't flip it. Cover your page now because the answers are going to be shown. They won't show up on my screen because they're programmed to come out one at a time. Do your first one here. I'm going to give you a couple seconds to do this one. Here's the question. Based on the Earth's radius, being an average value of 6.37 times 10 to the 6 meters, and its mass having a value of 5.98 times 10 to the 24th kilograms, calculate the value of the gravitational field strength at the Earth's surface. Okay? Now, something I didn't mention earlier about this pen. I can't just calculate the distance from the pen to the surface of the Earth. I have to calculate it from the center of the object that's creating the gravity. So at this point, I have to calculate the distance to the Earth's core. So it won't be the distance from here to the surface of the ground. It's going to be right from the point of the gravitational field where it begins, which is the core of the Earth. So in this case, we're trying to calculate gravitational field strength on the surface of the Earth at sea level based on the fact that the radius of the Earth from its center to the sea level is 6.37 times 10 to the 6 meters. It has a mass of 5.98 times 10 to the 24th kilograms. See if you can plug those numbers into the formula. See if you get an answer. Pause me right now. I'm going to go through the answer right now. Here's the answer. And if you've got your notes in front of you, you can reveal it in front of you. A lot of big numbers here. I'm going to plug it into my equation. Capital GM divided by R squared is going to be my equation for gravitational field strength. I'm going to plug in these numbers. Capital G, as always, is going to be 6.67 times 10 to the negative 11th newtons meters squared divided by kilograms squared, times that by the mass of the Earth, which is going to be 5.98 times 10 to the 24th kilograms. I'm going to multiply that together. Then I'm going to divide that. Once I've multiplied those two numbers together, I'm going to divide that by 6.37 times 10 to the 6th squared. If I plug all that into my calculator and I do it correctly, the answer I should have got in this case was 9.83 newtons per kilogram. All right? Interestingly enough, that number is very similar to the acceleration rate. You know this number if you've taken Science 10, if you've taken physics. This is why objects accelerate at a uniform rate when they're coming toward the Earth at just before ground level. That number is a number that you should already know, but we just calculated it using this actual gravitational field strength equation. Let's give you, and again, I just mentioned this, it's right here on the slide. It's worth noting that G is equal to the value of the gravitational acceleration on Earth, which is 9.83 meters per second squared. So therefore, in this case, little g actually also equals a at the surface of the Earth. Kind of an interesting side note for you physics buffs out there. Let's look at another equation here. Don't cover the answer. There's one more here for you. Here's another question. What about the gravitational field strength on the lunar surface? Let's go to the moon. Let's try to calculate the gravity on the moon. I've got a radius for the moon being 1.74 times 10 to the third kilometers. So 1.74 times 10 to the third kilometers. And it has a mass of 7.35 times 10 to the 22nd kilograms. Based on that, can you calculate the gravitational field strength on the surface of the moon? Pausing right now before I go through the answer. Here's the answer. Capital G, as always, is going to be 6.67 times 10 to the negative 11th newtons meters squared divided by kilograms squared, times that by the mass of the moon, which is going to be 7.35 times 10 to the 22nd kilograms. Multiply those two together, and then divide that by the square of 1.74 times 10 to the 6 meters. That should give you a value of 1.62 newtons per kilogram. Remember, if you've got an object that's outside of the Earth's orbit, then you would have to calculate the entire distance. So let's say a satellite. Let's say I'm using a satellite that's a very popular question amongst diploma exams. They'll use like a satellite in orbit around the Earth. What's the gravitational field strength where the satellite is? Well, then you'd have to calculate the radius of the Earth. They would give you a radius probably all the way out to the actual satellite. Again, the further away the object is from the Earth, in theory, the lower the gravitational field strength should be. And if you know that the gravitational field strength on the surface of the Earth is 9.83 newtons per kilogram, then you know that as you go further away from the Earth's surface, that number should get smaller. So that's a good indication if the question has to do with the Earth, that your number shouldn't get bigger than 9.83 newtons per kilogram if you remember what the acceleration factor is on the Earth, which is 9.83 meters per second squared. So that can help you out if the question has to do with the Earth, although in a lot of cases they'll give you a question about another planet or maybe another moon or something like that, just so that you're not having that information per se. Okay, now that I've got the information about gravitational field strength, I can also now calculate my gravitational force. My gravitational force, this is basically the number of newtons of force that's acting on the test body at that particular point. Well, gravitational force, which is in newtons, is going to be calculated by, now I have to not use the mass of the object that creates the gravity. Now I have to use the mass of the test body or the test object. So in the case of that question I was just using about the pen, right? If I wanted to calculate how many, what my gravitational force is on this pen right now, right beside the Earth, once I've calculated my gravitational field strength, which roughly at this point would be 9.83 kilograms or newtons per kilogram, I would use the mass of the pen to calculate into my gravitational force equation. So don't get confused. Even though you've got mass in your gravitational field strength equation and mass in the gravitational force equation, this mass is for the object that creates the gravity. This is the mass of the object that is responding to the gravity, which would be the test object or the test body. And then you would multiply that mass of the test body by the gravitational field strength that you've already calculated. So this is based on, you could have a two-part question here where they might give you all the distances and the weight of the test object and the weight of the object creating the gravity. You'd have to calculate this number first, my gravitational field strength, in order to then calculate my final answer, which would be my gravitational force. So you could see a two-part question like that where you'd have to calculate this before you calculate that. Let me give you an example of one. Here's an example. Based on the gravitational field strength that you calculated on the Earth's surface, remember that was 9.83 newtons per kilogram. That was the number we just got on the previous slide. Predict the force exerted on a person who weighs 100 kilograms. So give it a shot. Pause me, see what your answer is. Here it is. Well, because I already know, I know my mass, so my M is going to be 100 kilograms because again, my weight, my mass has to be in kilograms. And my gravitational field strength, which we already calculated on the surface of the Earth, is going to be 9.83 newtons per kilogram. I'm going to multiply 100 by 9.83, which is going to give me 983 newtons of force that's going to be exerted on that 100-gram individual. Remember, the bigger the test object, the more force is going to be exerted on that test object. The old adage, the bigger they are, the harder they fall. Really, that couldn't be more appropriate when dealing with this equation. Let's do one more. Let's calculate now the force exerted on that same person if they're on the lunar surface. Now you're going to have to use the number that we calculated for the lunar surfaces. We calculated the gravitational field strength for the lunar surface. See if you can calculate now the force that's being exerted on that person on the moon. Pause me if you need to. Here comes the answer. Here it is. Again, my gravitational field strength that we calculated on the previous page for the moon was 1.62 newtons per kilogram. I'm going to multiply that by 100 kilograms, which is the mass of the test object or the test body, in this case, the person. That's going to give me a number of 162 newtons of force that are going to be exerted on that person standing on the lunar surface. So you can see that there's obviously less force being exerted, gravitational force being exerted on the person on the moon, because there is less gravitational field strength on the moon. So that's why people on the moon are bouncing around. If you see the astronauts in the videos, they're very light because their mass hasn't changed, but their weight has. Remember, weight is basically represented by the amount of gravity. My mass doesn't change whether I'm on the moon or whether I'm on the Earth, but my relative weight will change based on how strong the gravity is that's basically pulling me down toward the object that's creating the gravity. All right, so those are your equations for gravitational field strength and gravitational force. Let's switch gears now to electrical fields and electrical force. Here are your equations for electrical fields, electrical field strength, and electrical force. Let's first discuss electrical field strength, which is arrow over E. The reason why there's an arrow over E is because we're already using E for energy, so we have to have a different designation for that E. So if you see the E with a little arrow on top of it, that represents electrical field strength. How do we calculate it? The formula is going to be KQ divided by radius squared. Well, K is going to be what's called Coulomb's constant, again, which is on page 2 of your data booklet. Coulomb's constant is found to be equal to 8.99 times 10 to the 9th newtons meters squared divided by Coulomb squared. It was calculated by our buddy Charles Coulomb, who had those units of charge named after him, coulombs. If you're interested to see how he did it, here's the video. They'll talk you through how Coulomb actually came up with the number and all of the things that he basically brought to the table when it came to early research on electrochemistry. So anyways, that's our K value, again on page 2 of the data booklet. Q we already know is going to be charge. That's going to be measured in coulombs, which we discussed last day, how we can measure charge of an object using coulombs. And then the radius squared is going to be the distance between the test object and the source of the charge. So if I've got a Van de Graaff generator over here, and I'm 5 meters away from the Van de Graaff generator. If I'm the test body that's being charged by the Van de Graaff generator because I'm in its electrical field, then the distance there would be 5 meters. Again, the distance is measured in meters, always in meters. You always have to calculate it. Your units for this plus gravitational field strength, you got to make sure that your distance and your mass units are correct. If you've got a question that gives you the mass in grams, and you have to calculate it to kilograms. If they give you a distance in kilometers, you would have to calculate it in meters for distance. So it's very important that you get the right units for each of the variables that are in the equations. Otherwise, your answers are going to be off by a factor, potentially of up to 1,000 or even 1,000,000, depending on how many variables the units aren't correct for. If I have, let's say, grams, and I've got milligrams, or sorry, grams, and let's say millimeters, then my values are going to be off by a lot if I plug those numbers in without converting them to the right units, which would be kilograms and meters, which you always have to use for. In the case of gravity, you would have to use kilograms. In this case, you have to make sure that you're in meters. You got to make sure you're in coulombs. So if they give you, let's say, microcoulombs or millicoulombs, you would have to convert that to coulombs. Your constant you'll never have to worry about because that number is always provided for you. All right. So so that's the equation. And again, it's basically what is electrical field strength, very similar to gravitational field strength. It's the number of newtons per coulomb that a test body experiences at a given location from a source of charge. That's basically the electrical field strength. So again, the more charge that's there, that's going to increase the higher the charge, of the object that generates the electricity or the electrical field. The bigger the charge, that's going to increase the electrical field strength. And the further I am away from that object that's generating the charge, or the test body is, the lower. So you've got a direct proportional relationship to the charge of the source. The higher the source of the source's charge is, the higher the field strength. If you've got a bigger distance, though, that's going to decrease. So there's an inverse proportional relationship between electrical field strength and distance. The further away you get from the object that generates the charge, the less the field strength will be. Let's apply that to an equation. Here's one right here. I got a Van de Graaff generator. Those suckers that actually, those big round balls on the top that you basically put your hand on, and they zap you and you get the hair all up in the air. You may have seen, Google it. If you haven't seen a Van de Graaff generator, Google one. They're a lot of fun. We have one at the school, that may or may not be broken at this time. Some years it works, some years it doesn't work. The beauty of having an old Van de Graaff generator. Anyways, that Van de Graaff generator has a charge of 0.0200 coulombs. Determine the strength of the electrical field from that Van de Graaff generator 20 meters away from the center of that generator. So if I've got a person that's standing 20 meters away from that Van de Graaff generator, and they're the test body, what field strength would I feel? What the field strength would be at that person where that test body is that's reacting with the Van de Graaff generator. Equations there. Cover the page. If you have to, pause me right now. I'm going to walk you through the answer right about now. Here's the answer. You're going to use Coulomb's constant to start off with, which is little k. That's going to be 8.99 times 10 to the 9th newtons meters squared divided by Coulomb squared. Times that by the charge of the Van de Graaff generator, which in this case is positive 0.200 coulombs. And then I'm going to multiply those together. Then I'm going to divide it by the square of 20 meters, which is my radius from the source of the charge. That should give me an answer of 4.50 times 10 to the 5th newtons per coulomb. And remember, just like gravitational field strength was newtons, newtons per, I got to cheat here, newtons per kilogram, newtons per kilogram. In this case, electrical field strength is going to be newtons per coulomb. So how many newtons per amount of charge are being exerted in that electrical field at that given point, okay? So that's how you calculate electrical field strength. And similarly to gravitational field strength, once I've known my electrical field strength, I can then calculate my electrical force. So once I know this, I can calculate the electrical force that's being exerted on a test body in the field. So in this case, what I'm going to have is I'm going to have my electrical force or electric force, which is going to be F subscript E or Fe. That's going to be in newtons. I'm going to calculate that by multiplying the electrical field strength, which is in newtons per coulomb, by the number of coulombs on the charged test body. So this would be just like it was in the gravitational field strength. This charge is no longer the Van de Graaff generator. This would be the charge of the test body. So if I'm the person standing 20 meters away from the Van de Graaff generator, it's my charge that I have to calculate at that point to see what the electrical force is that's hitting that test body. All right? So let's give you an example of that. Based on the electrical field strength we just calculated in the last question, you can cover this bottom of the page if you haven't already. Predict the electric force that's exerted on it. Let's say there's a second Van de Graaff generator that's 20 meters away. So I've got a Van de Graaff generator here. I got a Van de Graaff generator over here. They're 20 meters apart. I'm not worried about the charge of the Van de Graaff generator that's exerting the electrical force on the other Van de Graaff generator. I want to know, now in this case, it's an easy question because we're going to assume that both the Van de Graaff generators are generating the same charge. So both these Van de Graaff generators are running the same charge that we discussed in the previous question. So that makes it a little bit easier for your calculations. Try your calculations right now, see if it works. Pause me if you have to. Here's my, ready? Here we go. Here's how you calculate it. I'm going to use my formula. Fe equals electric field strength, E with the arrow over it, times charge or Q. What do I have? Well, I've got my electric field strength, which I already calculated in the previous question on the previous page, was 4.50 times 10 to the 5th newtons per coulomb. I'm going to times that by the charge that I'm assuming the other Van de Graaff generator has, because it's an identical one to the first one. So it's going to have the same charge, which is 0.0200 coulombs. If I multiply those two numbers together, I should get an Fe value of 9.00 times 10 to the 3rd newtons, or I could just write it down as 9,000 newtons. That would work too. So there's another thing for you. Whew, lots of math. 4 equations, and again, luckily, unlike the last equation that I gave you on the last slide or on the last video for 1.1, these equations are all in your data booklet, so you don't have to memorize them. You just have to know when and where to use them. Use the notes for heaven's sakes. Obviously, go through the textbook if you need to. Play the video again if you have to. But all the information is pretty much there. I'm going to finish up now with a little discussion about magnetic fields. Now, we're not going to do any calculations for magnetic fields. We're going to kind of just have a little discussion about magnetic fields on a planetary scale. As you might remember in my last video, I mentioned to you that electrical fields will generate magnetic fields and vice versa. Well, this is exactly what happens with the Earth. The Earth actually generates an electrical field inside of its core. And geologists believe this occurs because we've got a solid core on the inside of the Earth, which is surrounded by a liquid core that's actually in motion. And what this does is it creates a massive charge inside the core of the Earth. And this separates into separate layers because of the charge. And then as the Earth spins every day, because it spins once around its axis every 24 hours, hence we have a day every 24 hours, these charge layers are put into motion. And that generates an electrical field because we're moving charged particles. We're essentially creating an electrical current inside the core of the Earth. Well, because we're generating an electrical current, I just said that if we generate an electrical current or an electrical field, what we're going to do in turn is we're going to generate a magnetic field. So the Earth essentially is like a giant bar magnet. And as you're well aware, the Earth has a geographic North Pole and it has a geographic South Pole. And then you may have also heard of the magnetic North Pole and the magnetic South Pole, which are slightly off of the geographic North and South poles, respectively. Those are the top, that's the top and the bottom of the bar magnet that is the Earth. So, how does it work? Well, this is where it gets a little confusing. First of all, the geographic North Pole and the geographic South Pole do not line up directly with the magnetic North and South Pole, like I mentioned. But essentially, this this molten core in the middle here, this solid and molten core, becomes the epicenter or the starting point for these magnetic field lines that come out of the Earth. So they sort of come out of the center, and then they move up to the top, and then come back down here, and they come up from the top and down here, and they sort of extend, and they kind of create this magnetic field that basically surrounds the top of the Earth. The only place where the magnetic field is a little weak is directly over the North Poles. But over this side of the planet, there's a massive magnetic field here that sort of surrounds this side of the planet and this side of the planet. Now, you might have noticed something in my diagram. You might notice that on the diagram, it says here, this is the N and that is the S. Because remember, bar magnets, as I mentioned, have north and south poles, right? And we understand that a magnet always, the magnetic field lines always move from the north pole to the south pole. That's why you can see my arrows are pointing this way. But wait a second, this is the North Pole. So why is that the south and why is that the north? Well, North Pole, the geographic North Pole, the northern magnetic pole, it's only called the northern magnetic pole because of its geographical location. Technically, ready for this? Because this is where things get a little weird. Technically, the magnetic North Pole is actually the magnetic South Pole. The magnetic North Pole, or the northern magnetic pole, right now, if the Earth was a bar magnet, is actually the South Pole of the magnet. Yeah, a little weird. But here's where, well, put it to you this way. Here's how you prove it. Take out a compass. If you have a compass right now, take out your compass and tell me where the compass goes. Does the compass point to the north? Does the compass point to the north? Take out a compass. Try it out. Pause me right now. Find a compass. If you have a compass in your house, try it right now. It's because it's attracted to the South Pole. Anything that's magnetic is going to get moved in the direction of the currents of the magnetic field lines. So it is pointing north, but because it's in a magnetic field, it's showing us that it's pointing to the south because that's the way the magnetic field lines are moving that's the movement is moving toward that pole which is on the south end. If this was the North Pole and it was the magnetic North Pole, the actual North Pole of the magnets would actually point south. They wouldn't point north. So that's a way you can prove that actually the Earth right now, its poles have flipped. The North Pole is actually, the geographic North Pole is still the geographic North Pole. The northern magnetic pole site is still the northern magnetic pole site. But the magnetic polarity under that pole is technically the south pole of the magnet. That's what I'm trying to get at. And if you're interested about that, here's where it gets even weirder. Watch this video. The Earth is constantly flipping. There has been multiple times in the Earth's history where this magnet has actually flipped around on itself. And you watch this video because there's actually scientific proof. They discovered proof, and it's amazing how they find the proof of this because it's really cool how scientists discover this. But there has been multiple times in the Earth's history where the Earth's magnetic poles have flipped. And there's no reason to say why they wouldn't flip again at some point in the future. So take a watch that video. It's kind of an interesting one to watch. And then finally, well, is there a benefit to having this magnetic pole? Yeah, there is. The magnetic North Pole, or sorry, the magnetic field generated by the Earth is basically protecting us because right now the Earth is being bombarded. Even though the sun provides us with lots of energy that powers the planet and powers all the ecosystems on the planet, the sun also releases lots of dangerous electromagnetic radiation, which we'll be discussing in the second half of the unit when we discuss more about the electromagnetic spectrum. But the sun produces something called solar wind, and it also produces. It's similar to what are called cosmic rays, which are produced by other stars outside of our solar system. These cosmic rays are basically releasing ionized particles, ionized radiation that is basically lethal. These would be like things like gamma rays, X rays, high-end UV rays. We've discussed a little bit about that already, how the ozone layer protects us from these UVC rays, but the even more dangerous rays, like the gamma rays, the X rays that are being produced through the solar winds, that would be deadly to life on Earth. We're being protected by our magnetic shield. Our magnetic shield actually, as you can see in the image here, it actually it deflects the solar radiation around the planet. So it almost sort of bends these solar winds around us so that we don't actually, the surface of the Earth doesn't get hit by this really dangerous radiation. So without the magnetic shield around the Earth, we would be in a lot of trouble. We probably wouldn't be here because life would not be sustainable on the planet if we were bombarded by that solar radiation all the time. And the interesting thing is this, and this is really kind of where the whole the circle of force in the universe goes. The sun's solar winds that are produced by the sun are literally being ejected from the sun because of its own magnetic field. So the sun is producing these because of its magnetic field, and it has a massive magnetic field around it. And then the Earth is protecting us from these particles that are being ejected by a magnetic field from the sun by our own magnetic field. So there's a danger that's being caused by a magnetic field that's being solved by a magnetic field here on Earth. So kind of cool stuff. If you're interested to see a little bit more about that and the astronomy lesson that's related to that, watch that video. That's a great little video that will show you sort of where the solar winds come from and how our magnetic field actually protects us from those solar winds. That's it for today, folks. Thanks for tuning in. Here's your homework for tonight. Watch the complete practice questions, 12, 13, 14, 15, and 17 on pages 334 to 339, and answer questions 1, 2, and 3 on pages 346 to 347 in the Science 30 textbook. Next time, I'm going to be walking you through motors and generators, how we can use these wonderful devices to basically make electricity into motion, and how we can take motion and turn it into electricity for our own use. Won't you join me next time? Thanks a lot for tuning in, folks, and we will see you soon.